Hi everyone, we're going to continue on with chapter 8. So the lecture that we're covering today, there are going to be a few things that we've decided to eliminate. And if you're taking Organic 2, you will cover those in Organic 2. So I will mention them as we go through the lecture today. So we're going to start today with the hydrogenation of alkenes. So hydrogenation of an alkene is going to be a reduction process. The H2 is going to be added across the double bond. And it usually is going to require some catalyst containing compound. So the best type of catalysts are going to be, or that you guys will see will be platinum catalyst, palladium catalyst, which is probably the most common, and nickel catalyst. So what we have is if we have an alkene, so this alkene here, we have cis, this alkene here, we have trans. What's happening in both of these cases is we're going to be adding, so we have an H here, H here, H here, H here. So again, hydrogenation is just going to be the addition of H2 across that double bond. So in both cases, we really are going to have removal of the double bond, and then we will have addition of an H across, again, that double bond. So what really happens, so the mechanism for this is not covered, but I'll just give you kind of a general idea of what happens. So in this case, we're using this palladium on carbon. So this is a really common catalyst that is used for these types of reactions. What happens is the H2 is going to adhere to the surface of that catalyst, so the palladium catalyst in this case, and that's going to weaken that HH bond. The alkene is also going to adsorb onto the surface, and this is going to allow for H2 to add across the alkene on that adsorbed face. So again, this is going to be syn addition, so the hydrogens are adding at the same time, so they're going to be either both wedges or both dashes. So let's look at the stereochemistry a little bit closer. So if we have something that looks like this, and you see hydrogenation, so you see H2, and then you have some palladium, nickel, or platinum catalyst, what's going to happen is we're going to have addition of H2 across that double bond. So we have this possibility. We also would have this possibility. So in some cases, you can decide which would be the major contributor or major product that's being formed. So I'm sure you guys are thinking, since these are cyclohexane rings, what we could do is we could draw the chair conformation, and the one that is lower in energy, so less sterically hindered, would be more preferential for formation. So if we look here, we have, so this will give you guys a little refresher on your chair conformation. So remember, these are cis to each other, so both would be up. So we have up, up. So we have this in the axial position, we have this in the equatorial position. So remember, we have those 1,3 diaxial interactions. So we would only have a methyl hydrogen diaxial interaction in this case, so just one of them. When we look at this chair conformation, so we have up. So this one is pointing up, and then we will have this one here pointing down. So what we have is we have now both methyl groups in the axial. So again, axial, axial. So that means that we would have two CH3H types of 1,3 diaxial interactions. And remember that each one of these, so this one here is going to have two of its own, this one here would have two of its own. Same thing up here. So this one, even though we have one type of methyl group, it's going to have two different 1,3 diaxial interactions, right? So it will interact with the hydrogen in this position and the hydrogen in this position, for example. So when we're looking at the one that would be most likely to form in higher yield, it would be this product right here. And again, it's just because in chiral alkenes, the less sterically hindered face is going to absorb preferentially and accept that H2. So this chair conformation here is lower in energy. So again, it would just form the more stable product. So what we're going to actually skip is what we're looking at next. So the cyclopropanation of alkenes with carbenes. So this is going to be skipped. And again, this will be covered in Organic 2. So what this entails is the rest of page 14 in the notes is going to be skipped. It's labeled G, cyclopropanation of alkenes with carbenes. And page 15 is going to be skipped. Page 16 is going to be skipped. Again, these are all cyclopropanation reactions of alkenes. And then when we get to page 17, so what we're gonna do is we're gonna skip that top half, that Simmons-Smith cyclopropanation. That's also going to be skipped, but we're going to carry on with epoxidation with periacids. So this is important when you are covering your last lab. So for the last lab, if you have gotten to it or you may have not gotten to it yet, depending on where you are in the week. So epoxidation is something that you guys will be looking at, and then you're going to analyze the data by NMR and IR. So let's talk about the epoxidation. What is epoxidation? So we have epoxidation with periacids. So what a periacid is, it's really short for peroxide carboxylic acids. So what we have is we have to add an oxygen to an alkene, and this is going to lead to a 3-membered ring called an epoxide. So something like this would be called an epoxide. So again, 3-membered ring with an oxygen in it, and again, this is adding over that double bond. So we have 2 types of periacids that are commonly used for these types of reactions. So we have periacetic acid, which is going to be this right here, and then we have metachloroperoxide benzoic acid, which is shown here. So the one that you used or will be using when you're analyzing the data is this right here. So this is MCPBA is the abbreviation that is commonly used for this. And again, that's metachloroperoxide benzoic acid. If we look at the mechanism for this, so again, if I cover the mechanism, it's fair game for a mechanism type question. If we don't cover the mechanism, then you would never be asked to draw the mechanism for that specific reaction. So the mechanism for epoxidation reaction, so what we have is, let's look at that periacetic acid. And we have some alkene here. So what happens is this oxygen here is going to take on this hydrogen. This oxygen is going to put a set of lone pairs here to form a double bond. And what happens is we're going to form our 3-membered ring. So this carbon here is going to link with that oxygen. And then this oxygen here is going to link with this carbon right here. So this is going to result in our carboxylic acid byproduct. So again, this is a byproduct. This is our carboxylic acid. Remember, carboxylic acid is just COOH with some R group. And then what we're going to have in this case is going to be the formation of our epoxide. So with the formation of our epoxide, we're forming this 3-membered ring over this alkene right here. And then we have this R group coming off of it. So again, this is our epoxide. So when we're looking at the different examples, let's look at a few that we can look at with trans and cis types of isomers. So if we look at a cis versus trans alkene, so if we have something like this, we're using that MCPBA. Typical solvent is dichloromethane. And what would happen here, so again, we're going to form that epoxide over that double bond. So we're going to have, and again, these are trans to each other, right? This group and this group. So when we show our product, they're going to remain trans. So we can have this possibility, or we can have this possibility. So again, this indicates that these are going to be trans to each other. If we have a cis, it's going to retain that type of stereochemistry in the product also. So if we have MCPBA and dichloromethane, again, this is going to be cis, right? We have priorities 1 both facing in the same direction. So what will happen here is that our product would also be cis. So we have the product this product could possibly be formed, or we can have a formation of this product. But in either case, both of those R substituents are going to be cis to each other. The next thing that we're going to look at is going to be the dihydroxylation of alkenes. So what dihydroxylation of alkenes really means is it means that we're adding an OH group to each of the carbons from that alkene. So these are commonly called 1,2-diols. So when we're adding two different OH groups, again, they'll be called 1,2-diols. So if we look at the formation of trans 1,2-diols, so these are going to be anti-addition. So when we have anti-addition, what we do is we're going to synthesize these from the reaction of epoxides and water under acidic conditions. So if we look at this alkene here, so this first step should look familiar from what we just covered. So we have the periacetic acid. So we know we're going to form that epoxide from this step. And then what's going to happen, now we're adding water to it. So if you're thinking of what we've looked at before, right? So water indicates that we could have, that's going to be a nucleophile. So we can have an attack at one of our carbon atoms, right? So the two products that we would form in this case are going to be this product here. And I'll walk you guys through the mechanism also to kind of better explain this. So again, these are going to be trans to each other, right? So we have anti-addition. So we have one of the OHs as a wedge, one as a dash, and the opposite in its enantiomer. So one is the wedge, one is the dash. So let's look through the actual mechanism for this reaction. So what happens is, again, we're going to look here at this periacetic acid. So whenever you see that, you're going to have the formation of your three-membered ring. So I'm going to show it just with the wedge, but this would also happen with the dash, the same exact thing. So we have this plus its enantiomer, which again, the enantiomer would just be a dash in this position. Now what's going to happen, so remember our oxygen has two sets of lone pairs. We have this oxygen is going to take on this proton. So the reason that we're protonating the epoxide is because we're trying to make it a good leaving group. So what happens here is we're going to put a positive charge now onto our oxygen. Now that it's a positive charge, it's going to have some incentive to become a good leaving group. And we have water. So water is our nucleophile in this case. And remember that attack on the protonated epoxide is going to occur again at that more substituted carbon by a backside attack. Again, it's occurring at that more substituted carbon just because it has the greater positive charge on that carbon atom, and it's going to be a backside attack because as this bond is breaking, the water is coming in to attack that carbon atom. So after the attack of the water, what's going to happen is we will have the formation of this product here. So again, it's really important to think of, okay, I see the periacetic acid, so I know the first step is going to be the formation of that epoxide. And then when I'm looking at my water, so this is my nucleophile, water has to have a backside attack, which is why we have anti-addition. The reason it has that backside attack is because that CO bond is breaking as the water is coming in and attacking. So again, try to make sure you're understanding all the mechanisms. It will really help to think, okay, am I forming a trans 1,2-diol or am I forming a cis 1,2-diol? So the cis 1,2-diol we're going to talk about right now. So 1,2-diol, again, just means we're adding two OHs across that double bond. So when we have the formation of cis 1,2-diols, these are going to be syn addition. So this is both, so what's going to happen is both OH groups are going to be on the same face because again, it's syn addition. This is a one-step process. The most common reagent is going to be using a catalytical amount of osmium tetraoxide, which is just written like this. And then we use N-methylmorpholine N-oxide, which is shown as NMO. So whenever you see these two reagents, you're going to think, okay, I am forming the cis 1,2-diol. This is going to be one step. This is going to be syn addition. We won't actually cover the mechanism for this reaction, so it's not something that you need to know for the exam. Again, it's not something that was covered in any other past Orgo 1 class either. What happens here is if we have, again, this alkene here, we see our osmium tetraoxide and our NMO. We know, okay, that means we're gonna have addition of 2 OH groups and they have to be syn to each other. So we have the formation of this product plus the formation of this product right here. So both of these are possible products. And again, we will not be covering the mechanism for this reaction, but it is important to know. So try to kind of group things in your head as you're working through all of these reactions. Again, I know it's a ton of reactions for you guys to cover, and chapter 10 and 11 are going to be a lot more reactions that we're going to be working with. But what you really want to do is you want to try to group these as good as possible. So think of, okay, when I add 2 alcohols across an alkene, I have either cis or I have trans. If I have osmium tetraoxide and NMO, I know I'm going to put OH on the same face. If I have something like that periacetic acid or that MCPBA with the addition of water, I know that that's going to be a 2-step process, and it's a 2-step process, so I have that breaking of that CO bond while the water is coming in to attack, so I know that it has to be anti-addition. So lastly, we're going to cover the oxidative cleavage of alkenes. So we are going to skip a little bit of this. So we are going to look into cleaving an alkene into different carbonyl units. So remember, a carbonyl is just C double bond O. And again, this is called oxidative cleavage. We are going to skip oxidative cleavage with permanganate. So that's on page 19, the bottom half. And then that example on the top half of page 20, you will skip that in the partial notes. If you're interested in looking at it, again, it will be covered in Orgo 2 if you're taking Orgo 2, but the full notes will still provide all the information with the oxidative cleavage with permanganate. But we are going to look into oxidative cleavage with ozone. So we can use ozone to cleave double bonds to give both ketones and aldehydes. So ketone is going to be something like this. This is a really bad double bond. So that's going to be a ketone, remember, and then an aldehyde is going to be this group right here. So again, try to be as familiar as you can with all the terms that we use in Orgo 1, because in Orgo 2, it will definitely be expected to know all of the ketone, aldehyde, carboxylic acid, etc. So when we look at this reaction here, so what happens is ozone, again, as I mentioned, is going to cleave double bonds to give ketones and aldehydes. We can have no further oxidation. So ozone does not affect vinylic CH bonds. So what vinylic is, I think we mentioned this earlier on, but that's just this CH right here. So it's not going to further oxidize any vinylic or kind of capping CH bond. When we look at some examples of this, so let's look at a first example when we're have oxidative cleavage with ozone. So a common combination of reagents is going to be ozone and then dimethyl sulfide. If we look at our alkene, so we have this alkene right here. What's going to happen is you're actually, imagine like kind of chopping this alkene in half and capping it with a oxygen. So if we cut this in half right here, let's focus on this half first. So what we're going to have is we have this isopropyl here, and then we have this carbon. So this carbon right here is this carbon at the double bond. And then what we're going to do is we're just going to cap it with an oxygen. And then we're going to look at this half here, so the squared half, and we're going to do the same thing. So we're going to have this carbon here is going to be here, this carbon right here. Then we have this should be a hydrogen here. Then we have a hydrogen coming off of it. We have another hydrogen coming off of it right here. And then what we're gonna do is we're just gonna cap it with that oxygen. And that's again coming from the cleavage oxidation step of this over this alkene. When we look at another example, so let's look at this ring here. So we have a methyl group on this side, we have a proton on this side, we have ozone, and then we have our dimethyl sulfide. So again, what we're gonna do is we're gonna imagine kind of chopping this in half. We have our R group right here, or our methyl group, I should say. Then we're gonna have our oxygen. So the oxygen is in this position right here. And then what we're gonna have is we have our ring. We have, so now we're at this carbon right here. We're gonna have another double bond oxygen. And then we have a hydrogen capping this carbon right here. So remember, this hydrogen right here is not going to be further oxidized because ozone is a mild oxidant. What we can do, we can kind of rotate this bond just so it looks, we'll say, a little bit more normal to what we're used to. So rotation of the bonds would just give you this molecule right here. And it does help to number, so you can do like 1, 2, 3, 4, 5, 6, 7. Then we have 1, 2, 3, 4, 5, 6, 7. It may even help you do that over here. So if you number your methyl 1, 2, 3, 4, 5, 6, 7. So that means that you know that on carbon 2 and on carbon 7, that's where you're forming that carbonyl. So this is going to be it for chapter 8. So for chapter 8, again, I understand that there's a lot of mechanisms. You will be asked to kind of just like you were in chapter 6 and 7. So you can be asked to draw the products. You can be asked to write out the mechanism. You may even be asked to draw a stepwise reaction. So I can give you maybe a starting material and I can give you a product. And you guys can show me the maybe 2-step process or 3-step process to get to that final product. So all 3 of those types of questions are questions that you guys will see on the quiz. So again, practice, practice, practice. Try to group things, like I said earlier, with like the cis and trans diol. Think about the similarities, think about the differences between the two. With the cleavage, we only talked about really just with ozone. So again, you're not responsible for permanganate, but we also have, remember everything in the beginning. So we have the anti-Markovnikov addition when we're looking at HBr, for example, in the presence of a peroxide with heat or light, or we have the acid catalyzed addition of HX. So something like hydrobromic acid using just Markovnikov addition. So again, really look at the differences between the reagents and what type of product is forming. So do we have anti-Markovnikov or do we have Markovnikov addition? That's important to know. Also, it's important to know, do we have syn addition or do we have anti-addition? And again, if we talked about the mechanism, I recommend really understanding the mechanism because it will help you a lot when you're trying to draw out the products. But it will help you a lot also when you're trying to go maybe write a 2-step process to get to a final product if you really understand that mechanism. So again, practice, do Professor Rosenstein's, do Professor Madrick's, and please reach out to me with any questions. I hope you all are doing well. I miss seeing you all in class. Have a great day.